17, sir.
17th.
So
Sir.
17.
It's on 17.
17th. Okay, so 17th is Thursday. Okay, and timing is given. What timing is given?
The paper, the circular just says that we have to end it by 10 a.m.
Ended by 10 a.m. It has been written, is it?
Yes.
So we will have around 9 to 10. Okay, 1 hour examination we will have 9 to 10 on 17th. I will send a detailed notification on that. Another thing is I have just downloaded the attendance, this your roll list from ERP. So there are total 193 students are there. Okay. Can you see this roll list?
Yes, sir.
So there total 193 students are there. So I am going to send this roll list today along with 6 or 7 teams. Okay. So for instance 1 to 30 will be in they will be joining team 1, 31 to 60 will join team 2, etc., isn't it? So there will be 6 or 7 teams I am going to form, and that teams link also I will send in a separate document, separate Word document, and there I am going to mention only this information. I am going to mention the information that serial number 1 to 30 will be joining team 1. 31 to 60 will join team 2, something like that. Okay, and based on that you have to join a team during your examination time, and you have to keep your video on. Okay, you have to keep your video on, and you have to write your examination by keeping your video on the teams. But the examination will be conducted on Moodle, so both Moodle and team has to be kept on during the examination. Is it okay? Is it clear to everyone?
Yes, sir.
So I think you might have wrote the process control examination in the last semester in this manner, isn't it? So you all are aware, if I am not wrong somewhere, is it?
Yes, sir.
Okay. So again, one more thing is that there will be 7 to 8 PhD students along with me will be, monitoring the examination. And if I find anybody switched off his video, I will consider him as absent, and he will have to write the next examination. So anyway, we are having 3 examination, and base 2 we are going to select, isn't it? So even if you are missing any of the examination because of this non-compliance with the required conditions, then it doesn't matter. There is anyway one more examination is there, isn't it? So I am requesting all of you to keep your video on. If your video is not on, then the PhD student is going to mark you absent, even though you might submit your copy on Moodle, but I am not going to grade it. I am not going to grade it. We will consider it as absent. Is it clear to everyone?
Yes, sir.
Okay. Another thing.
Yes, sir.
So Utkarsh, you wrote something on Teams. What was the question? We will start with your question first, and then we will continue with our lecture. So you want me to present the earlier slides so that we can discuss? Hello?
I can type chat box.
Hello? Somebody is saying something?
So, sir, am I audible?
Yes,
Yes, sir.
you are audible.
Sir, I can type that here in the chat box, and
So
then
you have already wrote to me in a chat box, right? You said why we have considered this additional condition at the end, isn't it? That's what you said.
yes, sir. Yes, sir. Sir, there we have
Okay,
one
so
more
let me just
circle.
open that thing,
Process
and then we
control.
can discuss. Just a minute. Let me open the file. We can discuss the same. So is my slides visible to everyone? Hello.
Yes.
Yes, yes.
Okay, so the question from Utkarsh was, I will explain that question again. Just a minute, let me. Okay, that is not in conduction chapter. That is in the heat transfer coefficient. Okay, so let me just delete that transfer coefficient. Okay. So question from Utkarsh was this. What he was saying is, it visible to everyone, this slide? Hello?
Yes, sir.
Okay, so the question from him was why we have included this surface area in the heat transfer at the end, and why not we have not included this area while looking at this shell, isn't it? That's what the question is. So the answer is evident from the diagram itself. So Utkarsh, what is happening is when we are assuming this shell, you can see that the convection is occurring only from the outside surface. This particular surface will not be available for convection when we are looking at the shell in between here, isn't it? But when we reach to this end, then this additional surface becomes available. That's why this additional surface we have used when we are looking at the boundary condition.
Yes, sir.
Is it clear?
Yes, sir. Got it.
Remember, for convection, see, when we are assuming a shell balance here somewhere in between, then only whatever the outer surface we are, having, only that is available for convective heat transfer. This
Yes, sir.
particular surface area which will be here somewhere inside, that is not available for convection. That is available only for conduction. Anyway, in the conduction we are including that, isn't it?
Yes, sir.
You can see here that when we are looking at the heat loss from the convection, we are only taking this 2B plus W. So we are only taking the surrounding area. But this conduction area BW, this we are not including. This we are including only at the end when we are looking at the boundary condition somewhere here. Somewhere here we are including that. Okay, so for instance here you can see when we are considering this Qmax, in that Qmax this BW we are including, because there we are looking at this entire fin, isn't it? This entire fin we are looking at. There this additional surface BW is also coming into the picture, otherwise it's not coming, isn't it?
Yes,
Correct.
sir. Yes, sir.
Okay, so did I answer your question, or do you want some more discussion on this?
Yes, sir. Got it, sir. Got it.
Okay, all right.
Got it,
So
sir.
let me just again go back to where we have left in the last class. Okay. Okay. So in the last class, what we started looking at why the heat transfer coefficient is important. Then we said that this heat transfer coefficient will be varying locally. Then we said that since it is varying locally, typically an average heat transfer coefficient is used in the correlation, and that is what people generally calculate. Okay. So then for developing the correlation, remember we wanted to have the correlation for heat transfer coefficient. So this heat transfer coefficient correlations has to be in terms of the variables of interest, isn't it? So how this thing is done? This thing is done using dimensional analysis. So what we are saying is let's say if you wanted to develop a heat transfer coefficient correlation, then we need to find out what are the different variables which are going to have an impact on this. So typically that is done using experimental finding and the process understanding. Okay, and once we know all the variables which are important for a given system, then we can apply a dimensional analysis and we can find out what are the different dimensionless groups which are going to be important when we are looking at a particular heat transfer case. For instance, in the case of heat transfer through a circular pipe, what we have said is the variables of interest would be heat transfer coefficient, velocity, diameter, thermal conductivity, specific heat, rho, and viscosity, isn't it? So these are the variables which will be important. And how we have found out that these variables will be important? We have found out this using the experimental findings, and our understanding of the process. Okay, so once we have obtained this, then we can do a dimensional analysis and then we can find out what are the different dimensionless groups which are going to be important. Correct. So in this case, again, by applying the dimensionless analysis, what we have obtained is this Reynolds number, Prandtl number, and Nusselt number will be the three dimensionless groups which will be related with each other, and from this one has to find out the heat transfer coefficient correlation. Okay, so in a way, what we can say is heat transfer coefficient is present in this Nusselt number. So in a way, what we can say is Nusselt number will be related to Reynolds number and Prandtl number. How it will be related to Reynolds number and Prandtl number? Dimensionless analysis is silent on this particular fact. It only tells about what are the different dimensionless groups which will be related with each other and nothing more than that. Okay, but typically we see that in a pi flow, the Nusselt number is related by this type of equation, where a Nusselt number will be given as a polynomial function of Prandtl number and Reynolds number. And such relation we can also obtain by other method if we assume that heat transfer coefficient is related to all these variables in a polynomial fashion, the way it is shown here. So if we start with this assumption, then we can pinpointedly get such relation. Okay, but dimensionless analysis is silent on such relationships. Okay. So after getting the background about how the heat transfer correlations one should formulate, what should be the dimensionless groups which should be involved in these correlations, this we can obtain using this dimensionless analysis. The next step is what are the different dimensionless groups which are important in heat transfer. So we started with Nusselt number. We have defined the Nusselt number, and then we have defined Prandtl number, Reynolds number, Stanton number, Peclet number, and Garth number. And what we said is, depending on what type of system we are looking at for a heat transfer, one of these or multiple of these dimensionless groups will be important in the particular system. So for instance, if you are looking at the
Sir,
please go ahead.
Sir, the beta values which were in the formula for pipe flow for Nusselt number, which can be represented as in terms of yes sir, this slide, this beta 5 and beta 6, yeah, or all the values of beta, they should be like 1, 2, 3, 4, like or -1 integers, or like it can be.
So it depends. So see, once we have obtained this relationship, then we can find out beta 5 and beta 6 using regression. That's what is written. You generate the data and then you perform the regression and then you find out beta 5 and beta 6. So it could be a integer number, it could be a floating point number, doesn't matter. In fact, you look at for a pipe flow, this relationship is given as for a turbulent flow. If you are looking for turbulent flow through a circular pipe, what you get is Nusselt number is equals to 0.023, Prandtl number raised to the power 1/3, and Reynolds number raised to the power 0.8. That's what the relationship is obtained. This is nothing but a famous Ditters-Boelter equation, which we are going to see today. Is it clear to everyone?
Okay, sir.
So then we said that these are the different dimensionless groups. What we said is for a pipe flow, Nusselt number and Reynolds number and Prandtl number will be related. But if you look at the natural convection, in a natural convection, you will see that this Garth number or the other number like Rayleigh number, etc. is going to be more important. So anyway, depending on the situation, which Reynolds number, which dimensionless group will be important, that you will get to know as we progresses further. Okay, but these are some of the commonly used dimensionless groups in the heat transfer applications. Is it clear to everyone? Hello? Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, so we started with that. We started with the concept that we need a correlation for heat transfer coefficient. Then we said this heat transfer coefficient correlation we wanted in terms of dimensionless groups. So for that we have studied dimensional analysis. Then we said using the dimensional analysis, different dimensionless groups will be used. So we have looked at different dimensionless groups. Now thereafter what we have seen is how these correlations are developed. Okay, so far what we have done, we have here said that up to this we have said that the transfer coefficient is important and that has to be calculated using correlations. Then we said that the correlation should be in the form of these dimensionless groups. Okay, using dimensional analysis. Then we said that there are different dimensionless groups which are present in the heat transfer. And after this, what we are saying is how these correlations are developed actually. Okay, so this is also we have seen in the last class. What we said is for a simple example like double pipe heat exchanger. Of course, these correlations will be, specific to a particular geometry, particular flow type, or whether it's a internal flow or a external flow, different things will be there. But we have started looking at a very simple example of a double pipe heat exchanger where one fluid is flowing through a inner pipe and the other fluid is flowing through the outside annular region. Okay, how the dimensionless correlations can be, how the transfer correlations can be developed for such case. So in this case, you can see that in order to develop the correlations, we need to have variation in rho, mu, Cp and K so that the entire range of these variables should be included, isn't it? Remember, we have said that for a pipe flow, what are the variables which are important? Rho, mu, Cp, K, D and H, isn't it? Yes or no? That's what we have seen in the last slide, isn't it? Do you all agree or not? Hello?
Yes, sir.
So it is
We said here, we said that for a pipe flow, these are the variables which are important: H, V, D, K, Cp, rho, mu. Here H is the heat transfer coefficient which we wanted to evaluate, isn't it? That's why we are developing the correlation. But the effect of all these variables, V, D, K, Cp, rho and mu, effect of all these variables should be included in the correlation which we are developing for H, isn't it? So that means what? We need to perform the experiment by varying the value of D, by varying the value of K, by varying the value of Cp, by varying the value of density and by varying the value of viscosity. Do you all agree or not?
Yes, sir.
So that's what we are doing here. That is what precisely we are doing here. So we wanted to vary rho, mu, Cp and K. But rho, mu, Cp and K, these are the properties of the fluid. Yes or no? So that means by varying the rho, mu, Cp and K means what? We are basically changing fluids, isn't it? We are using different fluids to have the effect of variation in these properties. So we might perform the experiment with water. Then we might perform the experiment with some other solvent like glycerol or some other oil, isn't it? So we will have some variation in these properties by changing different fluids, by having large number of fluids in the experiment. Do you all agree? Yes or no?
Yes, sir.
Similarly, for varying diameter, we will have different pipes used here. For varying length, we can have, variable length. Sorry, for varying the velocity, we will have a different flow rate, isn't it?
Yes, sir.
So all these parameters we can vary, and then we can do a energy balance like this. And in this energy balance, we can calculate H using this formula. That's what we have seen. Here this delta T LMTD is coming in because here you can see the change in temperature at this location between hot and cold fluid, and change in the temperature between hot and cold fluid at this end. That means both these driving forces are varying as you are moving across the length. As you are moving from this end to this end, your driving force is not same. So in such cases, log mean temperature difference is used. So that's why here HA delta T LMTD is used instead of HA delta T. And this we will prove. This we will prove toward the end today, that in such cases the temperature has to be log mean temperature difference. So with this balance we can find out H. Now all these values of the variable we know, rho, mu, Cp, K, D we know, and we have also calculated H. Now we can calculate Nusselt number, we can calculate Reynolds number, we can calculate Prandtl number, and we can do a non-linear regression to find out this exponent alpha and beta, and even this constant C. Do you all agree or not? Correct?
Yes, sir.
And based on these, the correlations will be developed. But here you can see that we have used a specific form of correlation, but it's not required, as the dimensional analysis says that these correlations, what will be the relationship between these dimensionless group, it's not fixed. Only thing we can say with surety that these are the dimensionless groups which are related with each other. That's it. But how these are related, whether these are related by a power law relationship like this or not, it's not said. And that is why several correlations are developed which are not having the power law relation. For instance, you can see here this Hansen correlation, which is used for laminar flow through a circular pipe. Here this particular part is not a power law correlation, isn't it? It's not a power law correlation. Can you see? Is it clear?
Yes, sir. Yes.
Also, this 3.66 coming here, this is very important. This 3.66 has a physical significance. It's not arbitrary. This value 3.66 has a physical significance. So if you solve flow through a circular pipe for a very low Reynolds number, you will get Nusselt number equals to 3.66. That we will prove today. So for a constant temperature, you will get 3.66, and for a constant heat flux, you get 4.43 or something, if I'm not wrong. Let me just check. Yes, 4.364. That's what you are expected to get. And for a constant temperature, you get 3.66. For a constant wall heat flux, you will get 4.364. So there is some physical significance of these values which are added here. So in fact, in this particular equation, if you assume that Reynolds number is very low, this particular second term becomes 0 almost, and you get Nusselt number equals to 3.66. Is it clear to everyone?
Yes, sir.
Okay, so these are not arbitrary. Remember, even though there is some arbitrariness in how these dimensionless groups will be related with each other, there is some arbitrariness, because dimensional analysis is saying how these are related exactly, that is not known, isn't it? This could be related by any way, but within that also we are saying that the coefficient like this 3.66 has some physical significance. It's not arbitrary. It's not arbitrary. In fact, similar, if you look at the okay, maybe we will discuss it in the subsequent slide. So this particular Hansen correlation is valid when my flow is laminar. That means its Reynolds number is less than 2100. Also, the Nusselt number and Reynolds number here are calculated based on the diameter of the pipe. Okay, so again, another coefficient, another correlation is given by Sider and Tate. So Sider and Tate has given Nusselt number is related to Reynolds number and Prandtl number, and additionally this factor of mu by mu w raised to the power 0.14 is given. So this additional factor basically represent what? Whenever there is a large temperature difference between the bulk of the liquid and the wall of the wall temperature, in that case this correlation has to be used. Why? Because in that case the viscosity at the wall mu w and viscosity at the bulk will be very different. So this factor mu by mu W becomes important only when there is a large temperature difference between the bulk of the liquid and the wall of the pipe. And this particular correlation is valid for these ranges. When Prandtl number is between 0.48 and 16700, mu by mu W is between this range, and Peclet number into D by L is greater than 10 raised to the power 8. So only in that case this is valid, otherwise not. Okay. So another important correlations are Dittus-Boelter equation. So remember, these correlations are for laminar flow. These are for laminar flow. Okay. These two correlations are for laminar flow through circular pipe. Now this is also a circular pipe, but for a turbulent flow. For a turbulent flow, the most commonly used relation is the Dittus-Boelter equation. And this correlation you have to remember. This correlation very often people ask even in the interview, because this is so regularly used that every process engineer should remember this correlation, isn't it? So Dittus-Boelter equation is, Nusselt number is given as 0.023, Reynolds number raised to the power 0.8 and Prandtl number raised to the power either 0.4 or 0.3, depending on whether we are looking at heating of the fluid or a cooling of the fluid. If you are looking at the heating of the fluid, then this coefficient n is 0.4. If you are looking at cooling of the fluid, then this is 0.3, and this is valid for Prandtl number varying between 0.7 and 160. D by L should be less than 0.1, isn't it? And Reynolds number should be greater than 10,000. So what these things are giving? So remember, 0.7 to 160, that means there is not a large temperature difference between the wall of the fluid and the bulk of the fluid. That's what this particular first condition tells us. D by L is less than 0.1. What this second condition tells us? This second condition tells us that the flow is fully developed. When the flow is fully developed, you will you will have a fully developed flow when you are having D by L ratio less than 0.1. That means the length of the pipe is very large. So typically the flow is completely developed in such cases. And Reynolds number is greater than 10,000. That means the flow is turbulent. Can you see the importance of each of these conditions here? Hello? Am I making sense whatever I'm saying? Hello?
Yes, sure.
So there is another correlation given by Cedar and Tate. So this is for a turbulent flow. Now this correlation is similar to Dittus-Boelter equation, but this also account the large temperature difference. That's why this Prandtl number is changing from 0.7 to 16700. Here you can see that this additional factor mu by mu W raised to the power 0.14 is coming into the picture. So this particular factor becomes important when the viscosity of the fluid at the wall and the viscosity of the fluid at the bulk is different, isn't it? And when that can happen? Whenever there is a large temperature difference between the bulk of the liquid and the wall of the pipe, isn't it? Then and then only this factor mu by mu W is going to become more significant. Do you all agree? Yes or no? Viscosity of the liquid is going to decrease with increase in temperature, isn't it? So that means if the temperature of the wall is very large, that means this mu W will be smaller, isn't it? Compared to the bulk of the viscosity of the bulk of the liquid. Do you all agree? Hello?
Yes,
Does it
sir.
make sense?
Sir, could you please repeat the mu? Okay.
Okay, so what is mu? Mu is nothing but the viscosity of the bulk of the liquid. And mu W is nothing but, okay, maybe I'll just draw it. So let's say maybe I'll okay, so let me just draw roughly a pipe. This is, let's say, a pipe. Okay, let's say temperature here is 300. Okay, but the temperature of the bulk, T bulk is, let's say, 50 degrees Celsius. 50 degrees Celsius. Okay. So what will happen to the viscosity of the fluid at the wall and the viscosity of the fluid which is present in the bulk? What will happen?
So the viscosity of at the wall will be lesser than at the
And
bulk.
viscosity of the bulk will be higher. That means there will be a significant difference between these two values, isn't it? Correct.
Yes.
And viscosity also affects the heat transfer coefficient. Do you agree?
Yes, sir.
Isn't it? So that is why this additional factor is used by Cedar and Tate. So he is also accounting the change in the viscosity, because so see, ultimately heat transfer is taking place from what? Wall to the bulk. So that's what he is comparing, viscosity of wall and bulk, isn't it?
Okay, sir.
Is it clear?
Yes, sir.
Okay, so the slight difference here is, instead of 0.23 as that in the Dittus-Boelter equation is 0.27. Okay, that is the slight difference. And this Prandtl number raised to the power 0.33 always in this case, unlike 0.4 and 0.3 in earlier case. So in the Dittus-Boelter equation, this change in the viscosity effect is already embedded in this coefficient n. But again, this is valid only if the temperature difference between the two fluids is small. In that case, you will have a Prandtl number between this. Okay. Correct. But when we are having the large temperature difference, then the Prandtl number range is high. In such cases, one has to use a Cedar and Tate correlation instead of Dittus-Boelter equation. And both these correlations are applicable for turbulent flow through a circular pipe. There is another correlation by Seeban and Shimazaki. So this particular correlation is valid only for a liquid metals. This is valid only for liquid metals. So for a liquid metal, Nusselt number is given by 5 plus 0.025 Peclet number raised to the power 0.8. In fact, these three correlations will be useful in the tutorial problem which we have started in the last tutorial. That's why we have not done that problem, because these three correlations are required there. Is it clear? Again, one has to remember that this Peclet number is always used whenever we are talking about the heat transfer of the liquid metal. It is always represented in terms of Peclet number. Okay, you will see that liquid metals are always represented using Peclet number. So Peclet number is nothing but what? Reynolds number into Prandtl number. Okay, is it clear? Is it clear?
Yes, sir.
So why Peclet number? Now you may ask me why Peclet number is used in case of liquid metals, isn't it? That could be a question, and very often people ask in interview also. Why Peclet number is used for correlating liquid metals? Any answers on that? Can you say anything on that? Why Peclet number should be a more reasonable dimensionless number compared to a individual Reynolds number and Prandtl number? Remember, otherwise in all the correlations we are correlating Nusselt number with Reynolds number and Prandtl number individually. Can you say something on that?
So maybe because the Peclet number utilizes the heat transfer by conduction.
So that anyway we are including here both Prandtl number and Reynolds number, isn't it? Everywhere. And what is Peclet number? And Reynolds number into Prandtl number. The reason for using the Peclet number here is, if you calculate Reynolds number will be what? dV rho by mu. And the rho of liquid metal is very high. Density of liquid metal is very high, isn't it? So dV rho by mu. So Reynolds number you will get a very large value. And if you calculate a Prandtl number is what? Cp mu by K. Okay, so that you will get a lower value, but their multiplication becomes a reasonable. If you include that in this correlation, what will happen is Reynolds number is very small, whereas Prandtl number is, Reynolds number is very high and Prandtl number is very small, isn't it? So because of that, in order to avoid that bias of individual Reynolds number and Prandtl number, these are multiplied in a Peclet number, which gives a reasonable number. That's what the reason is. Okay. All right. Hello. Is my slides visible to everyone?
Yes, sir.
Hello.
Yes, sir. Yes.
Okay. So let's look at, okay, so again in the previous slide what we said that these correlations are developed for specific geometries, whether we are looking at cylindrical, spherical or flat. Also this could be for a pipe flow through a circular pipe, it could be for a non-circular pipe also, so a rectangular channel or the packed catalyst bed or maybe agitated vessel or even through a jacket, etc. Also it could be across the bundle of tubes, across the cylinder or across the spherical particles. Okay. So the flow could be internal, flow could be external. So internal means they flow through the pipe. External means flow across the pipe, isn't it? So different types of correlations people have developed for typical, shapes and the flow conditions. Okay, so let us start looking at heat transfer in a laminar flow tube. Remember I said that this correlation is this 3.66 has some physical meaning. It's not coming arbitrarily. So let's look at how we can find out the Nusselt number for a very simple case of laminar flow. And you can see that even for a very simple case of laminar flow, the mathematics becomes really complicated. Okay, so forget about solving a real life situation of turbulent flow. You will not be able to solve the flow and heat transfer problem together in such cases, because even though you may formulate the equation, but it is difficult to solve. So let's look at a very simple case. Very simple case is what? There is a pipe flow. This is the bigger pipe where the flow is occurring, isn't it? And we wanted to calculate how the heat transfer correlation is related in such cases. Okay, so flow is fully developed. Again, flow is laminar. The wall temperature is TW. Wall temperature is TW. The radius of the tube is R0. This radius is R0. Again, the velocity at the center, is U0. Okay, and the pressure is uniform across the cross section. So across this cross section, the pressure is uniform. The velocity distribution we can develop for the laminar flow. So the system is clear to everyone? Hello? Hello? Is the system clear to everyone? What we are saying?
Yes, sir.
Now in this case, again, as we can see that the velocity is varying and heat transfer will also be varying here. So let's assume a cylindrical shell. A cylindrical shell is assumed. So cylindrical shell of length delta x. So this length is delta x, isn't it? And the width also we will have, that width will be delta r width we can have here. Okay. Again, let's do the force balance first. So from the force balance we can obtain the velocity distribution first, and then we will solve the heat transfer problem. Right now we are trying to solve the flow problem first, then we will couple it with the heat transfer problem. Is it clear to everyone what we are saying? Is it clear? So we have assumed a shell of length delta x, isn't it? And this width here will be width of this. This is the annular shell. Remember, this will be an annular shell. Again here the width here will be delta r. Okay. So what will be the force balance on this shell? On this shell, the force balance will be what? So the pressure force acting here will be pi r square, isn't it? Sorry, P into pi r square. That will be the pressure force acting here, and the force acting on the other side will be P plus dP pi r square. Here dp will be the pressure drop, isn't it, across this thickness delta x. Again, the shear force will be acting in a opposite direction here. So shear force will be tau, nothing but the shear stress multiplied by the surface area. Okay. Is it clear? Is it clear to everyone?
Yes, sir.
Now the force balance here will be what? The force by a pressure drop pi r square dp will be balanced by a shear forces, isn't it? That is what will be balanced here, isn't it? So pi r square dp will be equals to tau into 2 pi r dx. Do you all agree? This type of balance you might have done in your transport phenomena to develop the velocity profile. We are exactly doing the same. We are trying to develop the velocity profile for a laminar flow by doing the force balance. Is it clear to you now? Just by looking at this equation. So whatever the pressure drop is going to happen between both these ends, that will be pi r squared dp, and this force by this pressure drop will be balanced by the shear stress here, isn't it? So shear force will be balanced by the pressure forces. So that's what we have written. Pressure forces will be pi r squared dp, whereas shear forces will be tau into 2 pi r dx, isn't it? This will be the circumferential area where the shear stress will be acting, isn't it? Yes or no?
Yes, sir.
Now here this tau we can replace by Newton's law of viscosity. So what is tau? Mu du by dr, isn't it? Mu du by dr will be the shear stress. That's what the Newton's law of viscosity is, correct? So we have put that here. Yes or no? Is it correct?
Yes, sir.
Now we can simplify this. So this mu du by dr is the shear force here. So now in this case we can rearrange everything. So after rearranging, what we get is du is given as 1 by 2 mu r dp by dx. This dp by dx dr. This is what we can obtain by rearranging. Do you all agree?
Yes, sir.
Isn't
Yes,
it?
sir.
And at any length x, we are assuming that this dp by dx is constant, isn't it? Pressure drop is constant at a particular x, isn't it? So dp by dx is a constant value. So pressure is gradually changing along the length. That's what we are saying from this equation, and that's a valid assumption. So with this, again, we can integrate this equation with respect to r. So what we are going to get, mu will be obtained as 1 by 4 mu dp by dx is a constant term that remains as it is. R dr integration of that will be r square plus constant. Do you all agree? This equation you agree? Isn't it? Do you all agree? Yes or no?
Yes, sir.
Okay. So after this, then you apply the boundary conditions. So what are the boundary conditions? At u equals to 0, r equals to r naught. At u equals to 0, r equals to r naught. So if you put u equals to 0 at r equals to r naught in this equation, what you get is this constant term comes out to be what? Minus 1 by 4 mu dp by dx r naught square. That's what you get, a constant term. Yes or no? And if you put that in this original equation, what we get is u is obtained as 1 by 4 mu dp by dx r square minus r naught square. Do you all agree?
Yes, sir.
Isn't it? And now we can put, okay, so at r equals to r naught, at r equals to 0, if you put it, what you get? You get the velocity at the center. So you get u naught you get as 1 by minus 1 by 4 mu dp by dx r naught square. This is what u naught, you get it. You put this u naught here, u by u naught comes out to be 1 minus r square by r naught square. This is the typical velocity profile. We get it for the laminar flow. Do you all agree? Equation 1, you all agree with equation 1? This is what you might have derived in your transport phenomena, isn't it?
So why is u not negative?
Put it here. What you are going to get?
No, sir. From equation it's coming negative,
Okay,
but
so,
what?
okay,
the
from
feeling-
why this negative value you are getting, you are saying, isn't it?
Yes, sir.
Okay, so see here in this case, basically if you look at, okay, so here in terms of dp by dx will be what? What dp by dx you are going to get?
Change in
Pressure is going
with
to be,
respect
pressure drop is going to be lower
Negative.
as you know.
Yes, sir. Yes, sir. Got
So
it.
that will
It's
be a
coming
negative sign there, isn't it? That
Yes, sir.
negative,
Yes,
negative
sir.
will get cancelled out. Is it clear?
Yes, sir.
All right. So mu by mu naught will be 1 minus r square by r naught square. And this is the typical velocity profile we see in laminar flow. So we have solved the velocity problem so far. Now we wanted to extend this analysis to a heat transfer problem. Okay. Is it clear? Okay, so this is the typical parabolic, profile which we usually see in a laminar flow. Now we wanted to solve a heat transfer problem for this particular case. Again, what we are assuming that we are solving this heat transfer problem for this assumption. Assumption is wall heat flux is 0. Wall heat flux is 0. So that means what we are assume that the constant heat flux at the tube wall. So that means dQw by dr is same as you are moving along the x. dQw here by dr is same as you move from one x to all, from one end to the other end. So in a way that can be represented in terms of this also. dQw by dx equals to 0. So that means what? Wall hit, this heat flux QW is not changing across the length. Is it clear to everyone? Hello? Is it clear or not clear? This particular part is clear or not clear? This is a very important assumption because then it simplifies your analysis significantly. What we are saying is okay, maybe I write down here. Maybe I write down, just give me a minute. Okay. So then this is a very interesting assumption. We are assuming what? What assumption we have made here? We said that wall heat flux is, we are saying that constant wall heat flux. This is what the assumption is, constant wall heat flux. That means what? QW is not varying with length x. Do you all agree? That's why dQw by dx equals to 0 we have used. But this gives a very interesting this gives a very interesting representation in terms of temperature. Okay, so what will be dt by dx? What will be dt by dx from this equation?
A constant.
This will be constant. Yes. This will be constant. Okay, correct. So that is what we have, used in subsequent slides. Okay, maybe I'll just erase this. Okay. Okay, so now let's look at the energy balance. Okay. So what will be the energy balance in this case? What will be the energy balance? So same annular shell we have, assumed, isn't it? So, okay. So this is the annular shell we have assumed. This is the same annular shell is assumed. So here there will be delta R thickness. Remember, now we are looking at the conduction along the radial direction. When we were looking at only when we are looking at here as a conduction in a radial direction, we are assuming a shell is a annular shell here, isn't it? So thickness of that shell is delta R. Okay. So now the heat conducted into the annular element will be what? dqr, isn't it? So dqr will be what? dqr will be what? In this case, you will have, okay, just a minute. So you will have the heat conducted into the annular element will be A into dqr. Okay. A into dqr. So there is something is missing. I will just add that. That should be there. Okay, this is missing here. Do you all agree?
Yes, sir.
Similarly, you will have, in fact, we will have DA. We should have DA instead of just A. So DA. So we should have DA into dqr. So that's what we have calculated. Okay. Similarly, here also we will have DA into dqr. But this will be calculated at R plus, isn't it? Do you all agree? Do you all agree?
Yes, sir.
Just a minute. I will take it. So this will be the heat input to the annular element. This will be the heat output to the annular element, and difference of that will be the accumulation in the annular element. So accumulation in the annular element is again given as 2 pi r dr dx cp mu rho u dot t by dx. Okay. So what we are doing here, you can see that this is nothing but volume. This volume, just a minute. So area is there. Okay. Area into velocity, if you do it, that gives a volumetric flow rate. Volumetric flow rate multiplied by this rho Cp mu, that gives us the mass flow rate, and Cp multiplied, that gives the energy, and then you are multiplying to T, isn't it? So this dx this get cancelled out. Okay, in a way. So if you look at in the right hand side, that is nothing but the amount that is being accumulated in the element. Do you all agree or not?
So where did the mu come from?
Where is the?
Mu, why we multiplied mu?
It's not mu, it's velocity u. It's a velocity u, it's not mu. Okay, so this 2 pi r dr will be what? Area. That area multiplied by u will be the volumetric flow rate. Volumetric flow rate multiplied by rho will be the mass flow rate. Mass flow rate multiplied by Cp will be the energy per kilojoule, isn't it? Multiplied by temperature will be the total energy, and this dx get cancelled out with this. So in a way, this is nothing but the energy which is accumulated in the element. Okay, is it clear? Is it clear to everyone?
Yes, sir.
So now we can rearrange everything. Now if we again in this entire thing, what we are assuming that this u is okay. So in this entire balance, if you look at, first we have found out the velocity profile, and now we are making the hit balance. But what we are assuming here is the velocity profile. See, heat transfer will also have a backward effect on the velocity profile, but that we have not included while calculating the velocity profile, isn't it? Yes or no? Did we account anything, any effect of temperature for calculating this?
No, sir.
Isn't it? But both are related, na? Momentum, see, the momentum transfer will also be affected by the temperature, isn't it? Now I am including this velocity here. I am including velocity here to find out the heat transfer, isn't it? So I am accounting the effect of velocity in calculating the temperature, but the effect of temperature will also be there backward on a velocity. But that we are not accounting. Can you see? Isn't it? That is the assumption we are using. You got the point what I'm saying?
No, sir.
Not clear. Okay. I am saying this is the pipe. In this pipe, if let's say the wall temperature is again 30 degrees Celsius, this is also in a 30 degrees Celsius. How my velocity profile will look? A parabolic it will be there, because both fluid and the wall is at 30 degrees Celsius. Do you agree? Do you agree?
Yes, sir. No.
But let's say now I am saying this temperature of this wall is 200 degrees Celsius, but temperature of the bulk of the fluid is, let's say, 25 degrees Celsius. Do I still get the parabolic profile?
No, sir.
So that effect I have not included. That's what I'm saying. You got the point now. I have not included the backward effect of the temperature on the velocity profile. I have not included. Ultimately, the viscosity here will be low. So instead of having the parabolic profile like this, you will have a slightly different profile in that case. So I am looking at the effect of velocity on temperature, but I am not looking at the effect of temperature on velocity. That's what I was trying to say here. Is it clear now what I'm saying?
Yes, sir.
Okay, so that effect we have neglected. So, okay, so again here, if we rearrange everything, after rearranging everything, what we get is dou by dou r dx dou t by dou r, and that is equals to r rho Cp mu by k. So this Cp mu by k we can represent as alpha, which is nothing but what? Thermal diffusivity, dou t by dou x dx. Okay. So dou t by dx, this anyway we are saying that this is a constant term. Remember in the last slide we said if the wall heat flux is constant, then dou t by dou x is a constant. Wall heat flux is constant. In that case, Q is not varying along the x. That means dou t by dou x is constant term. Do you all agree? This dou t by dou x is a constant term. Okay, so if we rearrange everything, what we get is 1 by ur dou by dou r, r dou t by dou r is equals to 1 by alpha dou t by dou x. This is what we have obtained from the heat balance. And now we have to solve this equation, because here we will have a variable u, and also we have to include the effect of viscosity, effect of velocity here, and then we have to solve this equation too in order to get the final expression. Do you agree? Do you all agree with me? Hello? Does it make sense what I'm saying? Something is not clear? At least up to this, everybody is okay? Up to equation number 2?
Yes, sir.
Okay, now let's try to solve this equation number 2. Okay, so we are saying that dou t by dou x will be a constant term. That's what we have proven earlier in the last slide, isn't it? If you take QW is constant across the length, then we can say that dou t by dou x is constant, isn't it? Now, since this dou t by dou x is a constant term, then everything is just a function of r only. We can solve this, isn't it? We can solve this differential equation. So dou t by dx is constant. In that case, then we can say that the temperature profile will be similar at various x. Okay, so dou t by dou r. Okay, so these are the boundary conditions. These are the boundary conditions. Okay, so boundary conditions for solving this equation are the change in the temperature dou t by dou r equals to 0 at r equals to 0. So this is the standard boundary condition we have used earlier also. Remember, we have used in when we have solved the expression for the cylindrical geometry, there also cylindrical or spherical geometry. We said that the change in the temperature at the center is going to be 0. So this is the typical boundary condition we have used. Also, the flux at the r equals to r naught will be just QW. So both these boundary condition we can use in this equation too, and we can solve this equation. So in this case, you can see that we will get a second order differential equation in r. This dou t by dou x is anyway is a constant term, so we don't have to worry about x. Is it clear to everyone? Now?
Yes, sir.
So we have rearranged this equation and we have inserted this u. This u we have already got the expression for u. So dou by dou r dou t by dou r equals to 1 by alpha dou t by dou x u naught 1 minus r square divided by r naught square r. And now we wanted to integrate it with respect to r. So after integrating with respect to r, what we get is r dou t by dou r, that is equals to 1 by alpha dou t by dou x. This is a constant term. Mu naught is also u naught is a constant term. So 1 by alpha dou t by dou x and u naught, this entire thing is a constant term. So that is taken as it is. What will be the integration of this term? This will be r, isn't it? R, if you multiply here, you will get r. Integration of r will be r square by 2, and this will be r cube. So what will be the integration of that? R raised to the power 4 divided by 4 r naught square. R naught square is again a constant term. Can you see this equation after integration plus integration constant? Is it clear?
Yes, sir.
Again, you can integrate, you can divide this r here. You will get r by 2 here and r cube term here, and C1 by r you will get, and then again you will integrate. So after integrating, what you get is t is given as 1 by alpha dou t by dou x u naught. This is a constant term, this entire thing constant term. Here you will get again r by 2, so that will be r square by 4 after integration. Here you will get r cube, so you will get again r raised to the power 4 16 r naught square, and this will be C1 by r, so that becomes C1 ln r plus C2. So after integrating, this is what you are going to get, a temperature profile. Is it clear to everyone?
Yes, sir.
Sorry. So now apply the boundary condition. If you put dou t by dou r equals to 0 at r equals to 0, what we get is C1 comes out to be 0, isn't it? Again, if you put the second boundary condition, so second boundary condition is what? Second boundary condition is k dou t by dou r equals to QW is constant, isn't it? But the second boundary condition anyway we have utilized. The second boundary condition anyway we have used for keeping this dou t by dou x as constant, isn't it? The second boundary condition itself is giving me this information, dou t by dou x is constant term. Do you all agree?
Yes, sir.
So that's why we require another boundary condition to solve this. It's not going to be useful. The second boundary condition will not be useful for getting the solution of this. So then again, let's say we know the temperature at the center, let's say is Tc. Let's say if you assume that the temperature at the center is Tc, then we can say that at R equals to 0, C2 will be just Tc. You will get the temperature you will get as a Tc here, isn't it? So by applying this, what you are going to get is T minus Tc. T minus Tc will be given as the same, this 1 by alpha dou T by dou x mu U0 divide U0 multiplied by R square by 4 minus R raised to the power 4 by 16 R naught square. So this is the expression which we have obtained, where Tc is the temperature at the center. Okay. So this is what the expression which we have obtained. Now what is our objective? So this is a simple case. Remember, this is just a simple case of laminar flow. That even for such a simple case of a laminar flow, when we are solving the equation analytically, see how complex things are becoming. Can you see the point?
Yes, yes, sir.
So if you solve it for a real life turbulent case, will you able to solve it? It's extremely difficult, isn't it? It's not easy to solve. Anyway, okay. So this is the expression which we have obtained. Our objective is to find out the heat transfer coefficient or a Nusselt number we wanted to calculate. Now, remember in the Nusselt number, Q is given by what? HA delta T, and delta T is what? TW minus TB, where TB is the bulk temperature. Now bulk temperature, how we can calculate a bulk temperature? Remember in the last tutorial we have discussed about the cup mixing temperature. So this is what nothing but the bulk temperature or a cup mixing temperature. So cup mixing temperature is nothing but the average over all the variables. So what are the variables? Rho, Cp, mu, K, velocity, isn't it? And temperature. Everything we have used here. So this temperature, bulk temperature, is averaged over energy. In a way it is averaged over energy. Can you see the point here? Hello?
Yes, sir.
That's why here you can see that the radius is varying, rho is varying, Cp is varying, mu is varying, and temperature is varying across the radius. So that's why the numerator is 0 to R0 2 pi R dr rho Cp mu T divided by denominator is 0 to integration 0 to R0 2 pi R dr rho Cp mu. Rho Cp U, sorry, this is not mu, this is U. Okay. Now put this temperature here. This temperature is what varying with the R. We can put this temperature expression here, and if we integrate, after integration, I have not done the integration, but if you do this integration, what you are going to get is the bulk temperature which you are going to get is this Tc plus 7 by 96 U0 R0 squared dou T by dou x divided by alpha. This is what you are going to get after integration, after performing this integration. Is it clear to everyone? You can do this integration yourself. You can put this T expression here and do the integration. Rho Cp will be a constant term. U is there, so U expression of U you have to put it here. So similar type of thing which we have solved in the tutorial, but there we had all the values, isn't it? So numerically we have just solved it using some computer or something, isn't it? Calculator or there, isn't it? But the analytical expression also you can obtain. So analytical expression we have obtained here is this. This is what the analytical expression you are going to get. Is it clear? Hello?
Yes, sir.
Is it becoming too much complex? Hello?
Yes, sir.
But
Yes, sir.
I understand it is becoming complex, but why I am trying to do this derivation is I am just trying to make you aware that even for a simple case of laminar flow, this is making our life really miserable, isn't it? So again, the another point for which we are deriving everything, because we wanted to see what is the significance of these values 3.66 and 4.364. These are the values, typical values when you get for a Nusselt number when a constant heat flux is there or a constant wall temperature is there. And you will see that for these two conditions, whenever people have wrote the correlations, these correlations are having these values as a starting values. For instance, you can see for a constant temperature thing, the correlation for a laminar flow is starting from this 3.66. You can see. Similarly, if you see the correlation for a constant heat flux, for a constant heat flux case, you will see 4.34 will be there as a starting value there. Okay, so there is some physical significance of that, and because of that, we are trying to derive from where these terms like 3.66 or 4.34 is coming. So that's why we have tried to derive it from the first principle. Okay, all right. So this is what the bulk or a cup mixing temperature which we have obtained. Again, the wall temperature we can directly obtain here. Wall temperature we can obtain directly by putting R equals to R naught. If you put R equals to R naught, we get a wall temperature from this equation number 3. So once we get the bulk temperature and wall temperature, both temperature we can subtract TW minus TB and multiply by H into A. That is going to give me a wall. That is going to give me a heat flux, isn't it? And this heat flux will be same as what? Ka dot T by dou R at R equals to R naught, isn't it? This is nothing but the heat transferred to the liquid from the wall, and that should be equals to the heat conducted at the wall, isn't it? Do you all agree or not? Again, this dou T by dou R we can directly obtain. We can differentiate this equation number 3 with respect to R and put R equals to R naught. We will get a dou T by dou R. So dou T by dou R comes out to be this equation. Mu naught R naught squared dou T by dou X 4 divided by 4 alpha. That's what you get dou T by dou R. And TW by TB, this you have already obtained from this equation, isn't it? So if you rearrange TW minus TB and dou T by dou R and multiply by K, what you get is H. So ultimately the H comes out to be 48K by 11 D naught. 48K by 11 D naught, that's what you are going to get. If you rearrange this H as in the form of Nusselt number, so Nusselt number is what? HD by K. So you can take D here and K divide here. So Nusselt number is HD by K, that comes out to be 48 by 11 itself. And that comes out to be 4.364. Okay, a numerical value you are getting. For a laminar flow with a constant wall heat flux, the Nusselt number comes out to be 4.364. Similarly, here we have started with the assumption. Here, remember, we started with this assumption dQ by dx equals to 0. But we could have started with the assumption that the wall temperature is constant. TW is constant. If you would have started with that assumption, we would have got Nusselt number equal to 3.66 directly. Okay. And you will see all the correlations written for laminar flow for a pipe flow. When we are looking at a constant wall heat flux, you will see this particular term. If you are looking at a constant wall temperature, you will see 3.66. Is it clear to everyone? Hello? Is it clear to everyone? Am I audible?
Yes.
Sorry. It's becoming too much complex, but we have done this example because we wanted to see what these numbers in these correlations actually why these specific numbers are used in the correlation. Okay, so that's what we have proven here, that 3.66 used in this correlation is not arbitrary, isn't it? That's what we have proven now. Correct? This 3.66 used here is not arbitrary. Isn't it? It has some basis. It's not arbitrary. Even though we are saying that the relationship between Nu, Nusselt number, Prandtl number, and Reynolds number can be arbitrary, but some of these terms here are not arbitrary. There is some basis for that. All right. Okay. So it is already 10:15. Let me check where we are. Okay, so let us stop here. We will continue from this point in the next class. I wish you all the best. So those who are attending the classes, thank you so much for attending the classes. Please go through all the slides which are already there. I am going to put these slides also in the Teams. you can download and you can go through. And those who are not attending, I am requesting them, if you are not attending, do not take this course lightly. Do not take this course lightly, because nobody is going to help you this time, because it is going to be a proctored examination. Unless you study hard, there is no way that you will score well. I want those who are, working hard, they should be rewarded. Because otherwise what happens is people do some tricks and they get the marks. I don't want that to happen. That's not the good thing, isn't it? If you are honorably studying, then definitely you should get the good marks, isn't it? And I am definitely like, if you are studying hard and if you are getting out of marks, I am happy. I am very much happy. But if you are not studying and if you are doing some, illegal means to get the marks, then I am not happy. Okay. Anyway, sorry. Okay. Is there any question?
Sir, will the syllabus of minor be till this
Syllabus
point
will
only?
be whatever we have covered till today.
Okay, sir.
That will be the syllabus. All the tutorial sheets I have already, put in a. I have already put it in a Teams. If you have not attended, still those solutions are already there. Okay. Again, all the class lectures we are recording. Even tutorials we are recording. So please go through everything I have given you. I have not kept anything with me now. I have given you everything and I am only asking you to please study. Please study and ask as many questions as possible to me. Okay. I am really happy to answer your question, because then it becomes, to and fro. Otherwise, only I am teaching to a wide screen here. There is no fun in that, isn't it? Unless you ask me something, I don't feel that I'm actually teaching to the students. Okay. All right.
So can you show that slide of force balance?
Yes, just a minute. Is my slides visible? This slide you are saying?
Sir. In this, DP should be from left side now. In the force balance, if we are writing positive, then.
So that negative sign get cancelled out with the negative sign is also there, isn't it? That's why the minus mu du by dr is there, isn't it?
So minus mu to we use for momentum, flux.
So Newton's law of viscosity is what? Tau is given as minus mu du by dr, na? You are absolutely correct. That minus sign I have, omitted in both the cases. Got the point? So remember, I have used here mu du by dx. I have not used that minus sign here. That minus sign will get cancelled out with the minus sign here. Is it clear now?
Yes, sir. So this tau is momentum flux, right? Or shear force?
Shear force. Shear stress, sorry. Tau is a shear stress here. So shear forces are balanced with the pressure forces. So what we are saying is, whatever the pressure drop is going to happen in this shell will be because of the dissipation by a shear stress. Isn't it?
Yes, sir.
That's what we are saying. And the minus sign will be, taken care here somewhere. If that is what the question is.
Wait. Also, sir, that QW boundary condition, why is it not useful? I mean,
because that boundary condition anyway we have used in this particular thing when we are saying that dt by dou t by dou x is a constant. That's what we have derived here, isn't it? QW by dx equals to 0. This can be represented as dt by dx equals to 0, isn't it? dt by dx equals to constant.
Yes, sir.
So that we have anyway accounted. Isn't it? So that's why that boundary condition is not useful here.
That constant would be 0 now.
No. dt by dx will be a constant. Is going to constant means dt by dx. This will be if you look at dt by dx. So what it means is it will be proportional linearly. So temperature change along the x direction will be linearly proportional. So if you look at the center temperature, it will be decreasing linearly along the x direction. That's what it means. Got the point? If you are saying something is constant, that means what? It is linearly changing, isn't it?
Yes, sir.
Is there any more question? Does it make sense what I'm saying? Hello?
Yes, sir. Okay.
Okay. Is there any more question
Hello?
from anyone?
Hello.
Please go ahead.
Sir, I had a question in the second question of the tutorial sheet 5.
Please go ahead.
In that question, there was oil flowing in a pipe, I think, and we had to find out if it was heating or not. So we found out dT by change of temperature with respect to time, and it was positive. So we considered that it was being heated. Temperature was increasing from the center to the wall. But after that, when we found out the heat flow, then we considered Q to be K dt by dt instead of minus K dt by dt, and temperature to be higher on the wall than in the bulk. So I'm not able to understand in which way the heat was moving in that
So
question.
heat is moving from wall to the bulk of the liquid. That's why that minus sign is not coming. So what it means is see, typically minus sign comes when your radius is increasing, your temperature is decreasing. Then minus sign is coming, isn't it? But in this case, is what is happening? As your radius is increasing, your temperature is increasing. That's why that minus sign is not there. Does it make sense now, Ayush?
Acha, so sir, it's not like that the minus sign will always be there and the function will take care of the direction.
No. Minus sign. See, the minus sign is so. See, what is the rationale behind putting the minus sign in this Fourier's law of heat conduction is what we are saying that in the direction of conduction, temperature is decreasing. That's what we are assuming. That's why that minus sign is coming. But in the direction, okay, in the direction, if you are looking at here, in this particular case, as R is, increasing, your temperature is increasing. So that means that minus sign will cancel out there, isn't it? Minus or minus, that will plus, isn't it?
Yes, sir. But I was saying at the wall, the temperature was 120 degrees Celsius.
Yes.
And at the center of the pipe, it was 60 degrees Celsius. 60 and in the bulk also, it was lower than 120.
Correct. So that means what? If your radius is increasing, remember radius at the center will be 0.
Yes.
Radius at the wall will be R0.
Yes.
As you are moving from 0 to R0, what will be the temperature of the fluid? It will be increasing.
It will increase, yes.
Correct. So what will be dou T by dou R? Or dt by dr?
It will be positive.
It will be positive, isn't it? That's what we are saying. That is what we are saying, right? Isn't it? And K dt by dr, that negative sign will not be there. Why it will not be there? Because anyway, the temperature is increasing as the radius is increasing.
Okay, so sir, the inside the pipe, if we consider, so heat won't flow from the wall to the center of the pipe.
It's flowing from wall to the center, yes. But we are in our analysis, we are looking at radius from 0 to R. If you take another variable, let's say from surface to from the surface to the center, then let's say if you take the x is varying instead of R and x is 0 at the surface and it is R at the center, then that minus sign will come. But that's not you are doing. You are doing it in a reverse way, right?
Yes.
So that anyway will get cancelled out then.
Okay.
Simply,
so, sir,
even in a differentiation, you try to understand in terms of differentiation. Okay, then there will not be any confusion. What you are trying to find out in a fixed law of conduction or any of these cases, you are trying to find out dt by dr. Isn't it?
Yes.
So dt by dr is basically what it means when you are differentiating something, what you are doing. You are finding out the slope.
Yes.
So that slope is positive or negative. That depends on whether you are increasing the t or whether you are decreasing the t with r. Yes or no?
Yes, sir.
Isn't it? In this case, we are saying that as you are increasing the t along with r, that means dt by dr will be positive.
Yes.
Isn't it? If it is, let's say the wall temperature would have been, let's say 20 degrees Celsius and the center would have been at 60 degrees Celsius, then the minus sign would have come there.
Oh, okay.
Okay.
So that minus sign would have been due to dt by dr being negative, right?
So no. So see, dt by dr, we are always saying that dt by dr, when we are looking at, when the temperature is increasing along the radius or length, then we will have positive. If it is decreasing along the length, then we will have negative. That's what we are saying. Okay. Typically, when we are applying the Fick's law to a solid body, what happens? The heat is being transferred from high temperature to the lower temperature, and there we are taking the x0 at the higher temperature and the x equals to L at the lower temperature, isn't it? So as you are moving along the direction of the conduction from x equals to 0 to L, your temperature is actually decreasing. That's why that minus sign is there.
So basically Q should be positive.
Basically we are saying that the heat will be always positive.
Okay.
So that positive and negative sign, it only indicates whether it is moving in which direction. That's it. Nothing more than that. Got the point? So whether it is coming from surrounding to the fluid or from fluid to surrounding, that will be decided by that minus sign. For instance, in this case, if you calculate a Q that comes out to be positive, that means the system is heated by the surrounding, isn't it? The fluid is being heated by the surrounding. So Q is positive. Q is getting added. But let's say if the surrounding is at a 20 degrees Celsius and the fluid is at 60 degrees Celsius, then you will get minus. So that means the heat is being transferred from fluid to the surrounding. Yes or no? It's only tells the direction. See, heat cannot be positive or negative. It's only tells the direction in which it is moving. Correct?
But sir, if dt by dt is negative, then we take minus sign, and if dt by dt is positive, then we take positive sign. Then so it won't come negative, na? Anyway.
So that's what I'm saying. That's what I'm saying. So see, ultimately Q heat cannot be positive or negative, isn't it? It will be always the it will be always the positive, isn't it? Only the negative sign or something that only tells the direction in which it is moving. Whether
Okay, sir. So we have to use this formula to get the magnitude and tell the direction by seeing which temperature is higher.
Correct. Yes. All right. Is there any question? Any further question? Hello? Is there any more question? If there is no question, I'm going to send all these documents, your roll list, and please look at your serial number, and based on that join the team link. Okay, that information, everything will be sent to you by email today. All right.
Okay.
Okay, so let us stop here and all the best to everyone. See you next week. Next week, Thursday, we will have a class, isn't it?
Thursday 17th we'll have our exam, I think, on this.
So no class next week?
I doubt.
Okay, all right. So next week we will meet again. Okay, all right.
Thank you, sir.
Thank you, everyone.
Thank you, sir.
Thank you, sir.